Alright, welcome to Unit 3, Up and Atom. In this unit, we're going to be looking at the atom and the periodic table. In fact, here it is in detail. So we're going to start off with making sure we understand what an atom is, how it's structured, how to draw that, and what happens when they're not stable. And then we're going to look at how do we arrange atoms of different elements, and that's where we're going to get into the periodic table and look at its structure and some of the patterns that pop up in it. So we're going to get started now with module 3.1, where we're going to look at atomic names and structure. So you can see there our learning intentions and success criteria. Feel free to pause the video and read through that, but we're going to get straight into it. So what is an atom? Well, an atom is the smallest unit of an element. It was first proposed by someone called Democritus, or Democritus, however you want to say it, back in ancient Greece. Now, atoms are often referred to as the building blocks of matter, and each element on the periodic table is composed of one type of atom, and you cannot break it down into a simpler substance, not without just turning it into sort of what we would call subatomic particles. So here's our atom, and you can see some of those particles already. So let's get into detail with them. So all matter is made up of atoms, and atoms themselves are made up of three key subatomic particles. There is protons, neutrons, and electrons. However, most of an atom actually happens to be empty space. In fact, if you can read through it here in the science snippet, but if an atom was the same size of the MCG, the Melbourne Cricket Ground, then the nucleus would be about the same size as like a frozen pea and sitting in the centre. As for the electrons, they would be just specks of dust floating around in the stands, and everything in between that pea in the centre and those flecks of dust in the stands would be absolutely nothing. It would be completely empty space. There was not going to be air in there because air is made up of different types of atoms like oxygen and nitrogen atoms, so that wouldn't be there. That would just be nothing, like the vacuum of outer space, except this is the empty space within an atom. So let's look in a bit more detail at those different parts. So atoms are composed of two regions. The first part is the nucleus, and that's the very center of the atom. That's where really all the mass of the atom actually comes from. And the other space that we've got is the electron cloud. That's the area around the nucleus that has it's most of the space of the atom. A lot of it is nothing, but within there is where you're likely to find your electrons, and you'll find your electrons hanging out at one or more different energy levels in that. So our first particle that we're going to look at is the proton. Now protons are positively charged. Really handy there. Protons are positively charged. You find your protons within your nucleus. So you find those protons within the atomic nucleus right in the center there. So here we've got our proton with a big plus in the middle because it is positively charged. Now, protons are not the only thing hanging out in the nucleus. We also have neutrons. So neutrons are, like I said, in the atomic nucleus. They're about the same mass as a proton. So here we've got just an orange ball, but you might notice there's no symbol on that. And that's because neutrons are not positively charged and they're not negatively charged. In fact, they are an uncharged particle. In fact, a handy way of remembering this is that neutrons are neutral. So neutrons are neutral, they have no charge. All right, so our last subatomic particle is electrons. Now electrons are not found in the nucleus. Rather, as you can see in the second dot point there, they're in shells that surround the atom nucleus. So in these sort of like different areas or zones around the nucleus is where you find different electrons. Electrons are the ones that are negatively charged. So electrons are negatively charged. They are absolutely tiny. If you had a proton and you split it into 1,800 pieces, just one of those pieces would have the same mass as the electron. So they're about 1/1800th the mass of a proton. So very, 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 very tiny. Now, if we are talking about an atom, Very specific with my language here, I'm saying atom, not ion. So if we're talking about an atom, then you can easily work out how many electrons you have, because in an atom, you will have the same number of electrons as you do protons. So the electrons are equal to the number of protons in an atom. And here is our electron here. Obviously, none of these have been to scale or even in reference to each other, because this would have to be a lot smaller to be the right scale with the protons picture. All right, so what is in the nucleus? Well, you remember you've got your protons and your neutrons there, and because you've got protons with a positive charge and neutrons that are neutral that have no charge, you'll end up overall with a positive charge. So overall, the nucleus has a positive charge. Now, it is very, very small and very, very dense. There's a lot of mass packed into a very tiny space, and pretty much everything that an atom weighs, all of its mass is just in that nucleus, because the electrons are so tiny, they just really don't count towards the final or overall mass of that atom. So protons and neutrons are the things that contribute to the mass of the atom, and they're found just in the nucleus. All right, and so what we might do is represent it like this. We've got a cluster of yellow positive protons and orange neutral neutrons. They're all clumped together. And in an atom, you would have that in the center, and your electrons would be whizzing around outside of that. A little bit like this. This is one way we can actually represent it. So surrounding the nucleus, like I was saying, is the electron cloud, and that is the area around the nucleus where electrons are likely to be found. We never necessarily know exactly where they are, but we know that they're somewhere in these regions and they'll be orbiting the nucleus. Now, electrons hang out at different levels. They're different energy levels depending on, obviously, how much energy each electron has. Electrons with less energy hang out closer to the nucleus, and the ones further away from the nucleus are the ones with more energy. So this is a very specific type of model over here that we've got drawn. It's called the Bohr model of the atom, named after Niels Bohr, who sort of was the one to invent it. So electrons live in these different shells. Now, how electrons live in those shells is very, very specific. And you can see on the side there is a little animation playing with electrons that are yellow negative dots being filled into different shells. And that's going to keep playing while I talk. But basically, you've got to remember that those shells are energy levels. And we start filling with the lowest energy level to begin with. So we're going to start right near the nucleus with shell 1. And as you keep filling, those shells or energy levels have more and more energy, and they fill up first 2 in the first shell, 8 into the second. Then something around shell 3 happens that's a bit odd, and you can put 8 in, but once you get to 8, you end up having a 4th shell and going up to that, instead of going to the maximum of 18 that the 3rd shell can actually hold. But we're going to get into that a little bit later. But basically, one thing you do need to know is as you're filling up those shells, whatever shell is currently the furthest one from the nucleus, that is what you call your valence shell. Valence sort of just means outermost in this case. So any electrons in that last shell are going to be called valence electrons. So there's a bit of a specific name for them there. So here's a bit of a summary of what we've been talking about. So you can see our nucleus is small and dense at the very center. It's in the middle of the atom, and most of the mass of the atom comes from it. In there you have protons, and they have a positive electrical charge. You also have neutrons, and they have no electrical charge, and they're about the same mass as a proton. Finally, whiz around the outside, you have electrons. They're contained within the electron cloud. They have a negative charge, and they're absolutely tiny, 1/1800th of the mass of a proton. And they're going to be, in an atom, they're going to be equal to the number of protons. So electrons and protons have the same amount of each other, as long as you're talking about just an atom. We will talk about a bit later when that changes. Alright, so I'm going to play a video for you now, just going into this and delving into how are atoms structured and what size they are.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? it would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, that's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
Alrighty, so let's jump back into looking at the atom's structure, because you see, not all atoms have the same number of protons. In fact, different elements have to have different numbers of protons. And they don't always have the same number of neutrons, and they don't always have the same number of electrons. And when you change them within an atom, interesting things happen. So remember, all atoms are made up of protons, neutrons, and electrons. And the amount you have of each of those is going to affect different properties of that atom. And you can change them. Now, if you change the number of protons, let's say you have something with 6 protons and you add a proton in and go up to having 7 protons, what you end up doing is you turn it into a different element. You see, if something's got 6 protons, it's an atom of carbon. But if you add another proton in and it has 7 protons, it now is an atom of nitrogen. So it becomes a completely different element. On the other hand, if you change any of the other two, you will not change the element. Okay, so the only way you can change what element you're talking about is actually by messing with the number of protons. So if you make a change to the number of neutrons, you get what we call a different isotope. Now, neutrons don't have any impact on the charge of the atom because they themselves don't have a charge, so they can't do anything. And what happens is you just add more mass to into the nucleus. And so we end up with what we call an isotope. Now, the word isotope means same place. It just means that these are things that will be the same element. So in the periodic table, that they will sit in the same place. So you could have carbon-12, which is one version of carbon, or you can have carbon-13. But both of them are carbon, and so on the periodic table, they take up the same place. And that's what isotope means. And the difference between them is they have different masses. So carbon-13 weighs 1 more than carbon-12. And this can actually end up giving quite drastically different properties to the atom. But we'll talk about that in a couple of modules' time. Finally, if you change the number of electrons, again, you do not change what element it is. But remember, electrons have a charge. So when you change the number of electrons that you've got, you're going to be messing with the charge. And so because the electrons are negative, if you get rid of them, overall things become more positive. But if you get an electron or several of them, overall things will become more negative. And what we say is when this happens, you've created an ion. So it's the same element, but now it's a charged version of that element, and it'll either be a positively charged or a negatively charged version of the element. It does depend on what element it is, whether it will become positive or negative. It doesn't do both, it does one or the other. So I'm going to go through a few new words, or hopefully maybe not that new, but the first one is atomic number. Now, atomic number is actually the number of protons that you have in the nucleus of an atom. And like I was saying before, when you change the number of protons, you're changing the element. And this is because protons are what is used to identify the different elements. Each element has a different number of protons. So we have an atomic number, and this is just how many protons there are in the nucleus. So for example, hydrogen's atomic number is 1 because it has 1 proton. Lithium's is 3 because it has 3 protons. Carbon is 12 because it has 12 protons. Oh, sorry, carbon is 6 because there's 6 protons. Its mass number is 12. That's on our next slide. And so you can go through, and if you're looking at the atomic number, that's how many protons it has. All right, so one thing to note, if you're looking at a periodic table and you've got 2 numbers there, first of all, your atomic number is always going to be a whole number. It's never going to have a decimal because you can't have parts of protons. You either have a proton or you don't. Okay, so if you actually have the atomic number, if you can then actually identify what element you're talking about. So, like I was talking about before by accident, mass numbers. Mass numbers are a bit different. So what you're doing here is you're actually going, well, how much is this going to weigh? And you can work this out by adding in the numbers of the 2 things that contribute to the overall mass of that atom. So the 2 things in the nucleus that are going to give or add to the mass of the atom are the protons and any neutrons that it has. So the atomic mass is the mass of the protons plus the mass of the neutrons. Now, if we each say that one proton has a mass of 1 and one neutron has a mass of 1 as well, then you can just basically count up how many there are of each. So remember, electrons are so small, they basically have a mass of 0, so we just don't count them. So what you could do is if you had, for example, fluorine has 9 protons, but it has 10 neutrons, or at least the isotope of it that I'm talking about. And so you would add those 2 together. So you go 9 plus 10, and that would give you 19. And so you get a mass number of 19 for fluorine. Now, as I just mentioned, that was for that isotope that I was talking about. But not all atoms of an element are exactly the same. They can vary slightly. So as I said earlier, atoms are the same element with the same number of protons, but they have different numbers of neutrons. This is an isotope. And you can see here it explains that iso is the Greek for same, and tope, or tope, comes from the Greek word for place. And so it's saying isotopes are atoms that live in the same place on the periodic table. So my example earlier was of carbon, but you can see here we've got one of hydrogen. We've got 3 isotopes of hydrogen: hydrogen 1, hydrogen 2, and hydrogen 3. Now, they're all hydrogen. Why? Because they all only have 1 proton, and that's what makes hydrogen hydrogen. But hydrogen 1 doesn't have any neutrons. Hydrogen 2 has 1 neutron, and hydrogen 3 has 2 neutrons. And so overall, if you look at the mass, hydrogen 1, its mass, because it only has a proton, is 1. Hydrogen 2 has 1 proton and 1 neutron, so you add them together and get 2. Hydrogen 3 has a mass of 3 because it has 1 proton and 2 neutrons, so you go 1 plus 2 is 3. And so they're all hydrogen, but they all have slightly different masses, and this actually does mean they behave in slightly different ways. But that's what an isotope is. They're elements or atoms of the same element, but they have different numbers of neutrons, and therefore they will have different masses. So it says there, notice the only change between each of those atoms is how many neutrons they have. All right. So what I want you to do now is have a look at this question. It wants you to work out the mass numbers for the different isotopes on the table. So remember, the mass number is the number of protons plus the number of neutrons. So pause the video and give that a go now. Alrighty, let's go through the answers here. So remember, mass number is equal to the number of protons plus the number of neutrons. So basically what you could do is you could say that here it's going to be 6 plus 6 equals 12. 6 plus 7 equals 13. 6 plus 8 equals 14. Alright, then we can move on to oxygen. Those first 3 were for carbon. Oxygen is here. We've got 8 plus 8 is equal to 16. 8 plus 9 is equal to 17. 8 plus 10 is equal to 18. Now we happen to have ones all in sequence, so you might not always get that, but that's all you have to do. Add the number of protons to the number of neutrons. Really handy because you can actually work it the other way. If you know the mass number and you know the number of protons, you can work out how many neutrons something must have as well. Though I do have a bit of a question for you. Now hydrogen has 3 isotopes. Each of them has a different mass number. And your periodic table has to have the mass number of an element on it. So how do we determine which one goes on the periodic table? Have a bit of a think about that. Pause the video if you need to, but have a little bit of a think. See if you can come up with a reason. It's a bit of a tricky one. And it's actually just something I wanted to touch on briefly. Because isotopes have different numbers of neutrons, they have different mass numbers. And so when you're looking at, say, 3 versions of hydrogen, and they each have different masses, you end up having to go with the one that's most common. And you do a bit of maths. It's a little bit like how when you get your final grade for a subject, that's based off a bunch of different pieces of work, but not everything is worth the same amount. And so an exam might be worth 30%, but a test might only be worth 10 or 20% or whatever it is. And so what you end up with at the end is not an average of all your grades, but rather what we call a weighted average, where some things contribute more to the final grade than others. Well, that's what we actually do for the periodic table, but we don't randomly pick numbers. It's actually got to do with how much there is of that type of isotope on Earth. So the more there is of one type of isotope, the more it has an impact on the final mass that we put on the periodic table. So if I jump back here, we have 3 isotopes of hydrogen, but most hydrogen on Earth is hydrogen 1. So when you look at the periodic table, the mass that's there is pretty much just 1, because hydrogen 2 and hydrogen 3, they're so little, they really don't have any impact at all on the final mass. So like I was saying, you need to take an average, but it's a specific average that's a weighted average, and you get what's called a relative atomic mass. It's relative to how much there is of the different kinds. So it's based on the percentages there. You can see here copper, it's talking about having two different kinds, copper 65 and copper 63. Copper 63 would contribute it'd be worth about 69% of the final weight, whereas copper 65 would only be worth 31%. So it's a bit like saying copper 63 is worth 69% of the final grade, whereas 65 is worth only 31%, except that final grade is actually the final mass number that we put on the periodic table. So this just goes through how you can calculate it. It's not massively important for you to know, but it is certainly interesting for you to understand a bit more about the periodic table. So you're welcome to read through this to get a bit of an understanding about it. But if you're finding it a bit confusing and it's a bit tricky, that's all good. We'll keep moving on. So I want to talk now about number of electrons. So in an atom, and I've sort of been really trying to emphasize this, in an atom, your number of protons will be equal to the number of electrons. And this is because an atom is what we call electrically neutral. Overall, atoms don't have any charge. So if you have 3 protons, that means you have a positive charge of 3. To completely counteract that, you need to have a negative charge of 3, which means you would need 3 electrons. So you end up with 3 protons and 3 electrons, and they completely counteract each other and neutralize each other, basically. So you can see down here it says if 20 protons are present in an atom, then 20 electrons are there to balance the overall charge of the atom. Atoms are neutral. Boron has an atomic number of 5. That means it has 5 protons, and because it's an atom, it must also have 5 electrons. Now, that is, like I was saying, I'm trying to really emphasize this, that is for an atom. If you start shifting how many electrons you have, either you get rid of some or you take some extra ones, then we don't call it an atom anymore, we call it an ion. I-O-N, ion. And an ion, the number of protons is different to the number of electrons. You've either gotten more electrons or you've gotten rid of some and lost some. Now, a lot of people get confused because this next little bit feels a bit backwards, but remember, electrons have a negative charge, and so when you get rid of them, you end up with actually more positive charges because you've got now more protons than there are electrons. So overall, when you lose an electron, the atom becomes positive. On the other hand, because electrons are negative, when you get extra electrons, now you have more negative charges than you do positive charges, so you end up being more negative when you gain electrons. All right, so we've got a little bit of a video here just going through that.
Sometimes we draw atoms as balls with smooth surfaces, but they are a bit more complex than that. There is a nucleus in the center and a cloud of electrons swarming around it. And the electron cloud itself is divided into electron shells. The outermost electrons, the valence electrons, are the reason why chemical reactions occur at all. Smaller atoms with only 1 electron shell can hold a maximum of 2 electrons. In the larger atoms, the valence shell can hold a maximum of 8 electrons, no matter how large the atoms get. There is something special with having exactly 8 valence electrons. It gives the atom a kind of stability. Here is a chlorine atom. It starts out with 7 electrons in its outer shell. If it could only get 1 more, it would reach that magical number of stability. It wants an extra electron so much that it can pull it away from almost any other substance. That is why chlorine is so reactive. The chlorine atom is neutral to start with. It has the same amount of positive protons and negative electrons. When it gets that extra electron, it becomes a negative ion with a charge of -1. We write it as Cl-. As an ion, it's not reactive at all. Now that it has 8 electrons in its outer shell, it doesn't need to steal any more electrons. Some atoms change their name slightly when forming ions. The ion of chlorine is called a chloride ion. Here's another atom, oxygen. It starts out with 6 electrons in its outer shell, so it wants to get 2 more to reach that magic number of 8. When it picks up 2 electrons, it gets a charge of -2. The ion is called an oxide ion. We write it like this, O2 minus. So, when an atom has an almost full outer shell, it wants to take up more electrons. But what about atoms that start out with just a few electrons in their outer shell? Let's look at aluminium. It has 3 electrons in its outer shell. You'd think that getting 5 more would do the trick, but there are limits to how many extra electrons atoms can get. What the aluminium atom can do instead is get rid of its valence electrons. This is how all the metals form ions. Does that mean that it now has 0 electrons in its outer shell? No, look, as the electrons from the third shell go away, the second shell becomes the outer shell, and that had 8 electrons to start with. When an atom loses electrons, as metal atoms do, it becomes a positively charged ion. The aluminium atom loses 3 electrons, so its charge becomes plus 3. We write it like this, Al3+. Atoms that form positive ions don't change their names, so this is simply called an aluminium ion. Many of the elements around us usually exist in their ionic form, and ions are just like atoms, only with extra or fewer electrons.
So this last little bit really just wants to go through, if you were asked how many protons does this have, or how many neutrons, or how many electrons, this last couple of slides goes through that, and then we've got a bit of a question for you to practice on. So if you're asked to find the number of protons, what you need to do is find the atomic number. And that number is the number of protons. And that's all you need to do. So hydrogen's atomic number is 1, so hydrogen has 1 proton. Carbon's atomic number is 6, so carbon has 6 protons. So protons are really easy to work out how many there are of them. On the other hand, if you want to work out how many neutrons there are, you need 2 pieces of information. You need to find the atomic number and the mass number of the isotope you're talking about. Sometimes you might get told something like carbon-12 or carbon-13. The number on the end is the mass number for that isotope. Otherwise, you can just use what's on the periodic table. So what you need to do, once you have those 2 numbers, you need to subtract your atomic number from the mass number. The reason is that atomic number, remember, is the number of protons. So if mass number is made up of both protons and neutrons. If you take the number of neutrons out of that, you're left with the number of neutrons. So our example there says lithium has a mass number of 7 and an atomic number of 3. So that must mean you have 3 protons, because that's what the atomic number is. And so to work out the neutrons, we can go mass number, which is 7, minus protons, which is 3. So 7 minus 3 is 4. So lithium must have 4 neutrons. All right, so calculating the number of electrons, I've got this done 2 different ways, and that's because you might need to do it for an atom, or you might need to do it for an ion. So if it's an atom, again, super easy. Find the atomic number, and that's it. That's all you need to do, because it's going to be exactly the same as that, because it's going to be even to the number of protons. So hydrogen's atomic number is 1. That means it has 1 proton, and therefore, by default, also has 1 electron. Carbon's atomic number is 6, so it must also have 6 electrons. Now, ions are where things get interesting. What I would suggest you do, first of all, is work out, if this was an atom, how many would it have? And then look at the little plus or minus sign you're going to see next to the letters. So you can see down the bottom, we've got Mg2+. Okay, you will always have, if it's an ion, a symbol there, and you may or may not have a number. If you don't have a number, that just means 1. If there's only a charge of +1 or -1, then we just don't write the 1 in, we just write plus or minus. Okay, now if you see a negative sign, you actually need to add electrons. If there's 1 negative sign or just a negative sign, you add 1 electron. If there's 2 and then a negative, you add 2 electrons. Okay. On the other hand, if you see a plus, okay, that means you need to actually subtract electrons. So if you have just the plus by itself, it's just take away 1 electron. If you have a 2+, you need to take away 2 electrons. If you have a 3+, you need to take away 3 electrons. So find the number of electrons that it would have if it was just an atom. So you can see from the example before, it said carbon, its atomic number is 6, so it must have 6 electrons. Well, if carbon was an ion, you would then alter the number of electrons from that original 6. So our example down the bottom is magnesium. Magnesium's atomic number is 12. So a magnesium atom has 12 protons and therefore 12 electrons. But this then is an ion because it says 2 plus next to it. So we have to, because it's a plus, we have to take away electrons, and there's a 2 there, so we have to take away 2 electrons. So we started with 12 electrons, and we're now going to take away 2 of them. So when we do that, we are left with 10 electrons. And so that's how you can work out how many electrons you're going to have in an ion. Obviously, if they'd been a negative sign, you would have had to add on the appropriate number of electrons instead of subtracting them. So here is a table with a bunch of different scenarios. For each of them, you need to work out how many protons, how many neutrons, and how many electrons. So take what you've just learned on the past 2 slides and the rest of the PowerPoint, pause the video and fill the table in. So pause the video now. Alrighty, let's go through these. I'm actually going to do the first column, number of protons, just all together. So hopefully you remember, number of protons, really easy. Look at the atomic number. So all we have to do is look at this column here. Okay, and so we just basically fill that across. So it's going to be 11, 11, 6, 7, 9, and 8. All right, so easy peasy. Now when we get to the number of neutrons is going to be mass number here, and then take away atomic number. So we've got 23, take away 11 is going to leave us with 12. It's same for the next one, it's also 12. Then 12 minus 6 is 6. 14 minus 7 is 7. 19 minus 9 is 10. And 16 minus 8 is 8. All right, so moving on to our last column, when we're looking at number of electrons, if they're a normal atom, it's really easy. If they're an ion, there's a bit more work involved. So the ions that we have are the second one and the 2 last ones. So we're going to leave them for last. We'll do the other 3 really quickly. So all we have to do for the other 3 is copy what's in the proton column. So it should be 11 and then 6 here and 7 here. Now, for those other 3, the first one's actually set up to help you. So you have normally, as you can see in the line above, 11 electrons, but it's got a little plus. And so that tells us we actually need to take away electrons. And now there's no number, so that tells me it must be 1. So I need to take, from 11, I need to take away 1 electron. So 11 minus 1 is 10. All right, jumping to the bottom. So fluorine would normally have 9. I can see that because it's how many protons it would normally have, but it's got a negative. So negative means I need to add electrons, and there's only 1 negative sign, so I need to add 1 electron to 9. So 9 plus 1 is 10. All right, last one, oxygen. Oxygen, similar to fluorine, it needs to have electrons added, but this time we need to add 2. And what we need to do is we need to work out, normally it would have 8 electrons because it has 8 protons. So we're going to add 2 to 8. 2 to 8 is 10. And there we go. That's it. That's all done and dusted. So that is the end of this module. Thanks for watching. If you had anything you didn't understand, feel free to re-watch the video, speed it up, slow it down, jump back and forth as you need. And if you do have any questions still at the end of it, remember to speak to your teacher and let them know that you need some help and get that help that you need. Anyway, thanks for watching the video, and I will see you in the next one. Bye.